So my name is Joshua Saxe. I'm going to talk about our project called CrowdSource. Collaborators in this project are Raphael Turner, Christina Blokin, and Jose Nazario. I'm up here speaking, but they all made big contributions to this work. Christina and Raphael are back in DC, where our office is, but Jose is out here and may be out there in the audience. Maybe, not sure if he's here right now or not. But so the work I'm going to talk about today was funded under the DARPA Cyber Fast Track program. This is a program by which DARPA, which is the research arm of the Department of Defense, gets projects off the ground really quickly that they think could make a contribution to the security community. And our project is, the goal of our project is, given a large corpus of malicious software, we would like to quickly generate an accurate high-level reverse engineering report without the aid of a human analyst using a machine learning model trained on documents from the web. So I'm going to go over, so first the outline of the presentation. So I'm going to go over our motivation. Why is this? Why are we doing this? Why is it important? The algorithms, our method, and the impact that we think we can have on the open source. So this is an open source contribution to the security community. We're going to be releasing it in November. One goal of this presentation is hopefully to get people to use the tool and also to contribute. If people out there do malware reverse engineering or machine learning, we would love people to join as contributors. So the motivation for those of you in the audience who do malware analysis should be pretty familiar. There is an enormous volume of new malware being produced every day. This is just a screenshot of Virus Total. It's a site where you can upload a suspected malware sample. They get about 600,000 novel binary artifacts every week. This is according to their site last week. So that's a whole lot of new unknown binary artifacts that they're getting, many of which are detected, some of which are detected by AV engines and some of which aren't, many of which are probably malware. According to Center for Strategic and International Studies, malware is causing between $300 billion and $1 trillion in damages every year, and yet we don't actually understand malware very well, right? So if you actually look up, if your AV system detects that a binary artifact is malware, often you go to the site and look for a description, and you see no description available for most of the detections. That's actually the case. So sort of like we're dealing with a vast unknown ocean of malicious stuff that's causing pretty serious impact to computing systems around the world, and we don't really know what's going on. So there's a need for, so there's really no way that we're going to get reverse engineers just to take those 300,000 samples that are observed every week and reverse them, or that's sort of a fool's errand. It would be nice to automate the process, right? So that's the motivation for this work. Actually last year, we presented a project, we presented this project at Black Hat at Arsenal, where we clustered together malware samples. So sort of like what the previous presentation was talking about in terms of clustering botnet behavior on network activity. We looked at binary traces, dynamic traces of malware, clustered them together, and allowed this kind of view of the malware. We're pretty successful in clustering together samples and creating a useful view that shows similarity relationships between malware samples. But what we couldn't really do in that project was generate good, actionable, high-level reports about what the malware is doing. What we did in that project was create a bunch of expert rules that we used to just say, okay, well, if this API call is observed, or if this protocol string is observed, we think that it's doing it started a new process or something like that, right? That's the kind of level of detection that most of these rule-based systems are at. So that they can tell you that a malware sample dropped a bunch of files on the hard drive or launched a bunch of new processes. That's not really telling you how it's threatening your network or how it might affect a victim's machine, right? Like the kind of intelligence we actually need is more like it's exfiltrating data from users' keyboards out to China, right? These are the kinds of determinations we need to be generated in an automated fashion. We've also done some other visualization work. This is a kind of map of a very large corpus of malware that we generated. So in this map, each rectangle is an individual malware sample. And the samples that have similar colors and are adjacent to one another, our algorithm is estimating that they share code. So a lot of malware, as we all know, are actually polymorphic variants of one another or near duplicates of one another. This is a way of visualizing that sort of cluster structure in a malware corpus. So that's just previous work to frame the work that I'm going to talk about today. So the missing piece of the malware, the automated analysis research, we believe, is that we need to answer these questions. Like, what does the malware actually do? Does it log my keystrokes? Is it taking a screen capture? Is it capturing my webcam? How is it controlling this? How is it controlling the victim machine? Is it using a secure shell or a remote desktop? We need to be able to answer those questions in an automated fashion, and doing that is actually extremely hard. And most people, the current technologies are using expert rules, regexes, these kinds of things, and it's just really time consuming to generate enough expert rules and to keep up with changing APIs, changing programming environments. Now there's malware in JavaScript. Are you going to write expert rules for that? We wanted to take a different approach that uses a machine learning approach, so that you don't have to write expert rules, but that we learn automatically how to automatically reverse engineer the malware. So the structure of our project is we're leveraging existing technologies to do disassembly and unpacking. So we're using CuckooBox, thanks to the CuckooBox authors for that great open source project to run and unpack the malware. And then the piece that's really new is the analytics piece. And that's the machine learning piece that I'm going to talk about in a second. And you can think of this piece as really, we're attempting to replace the junior reverse engineer looking at the IDA Pro dump of the malware. We're attempting to replace her or him with an algorithm, basically. And you could say that might threaten people's job security, but there's enough work in cybersecurity that we can move on to more interesting problems than reversing your run-of-the-mill crimeware, malware that steals your banking credentials, that kind of thing. We would like to replace that with a machine learning system. And just to give you a sneak preview of where this talk is going before I get bogged down in the math and the data sets that we're using and that kind of thing, this is the kind of output that we're currently generating. So given a malware sample, we ingest it into the system, and in about 200 milliseconds or so we spit out a report like this, where we usually detect many more capabilities than this, but here's a detection that the malware is using webcam spying. We're able to associate API calls automatically with that capability, and then actually we're able to associate documents from the web that give proof that API call is actually associated with that capability. So, for example, here we've detected create capture window A. Turns out that's an API call in the Win32 API call to tap into the webcam, right? So our machine learning model has automatically discovered that and associated it with the malware. So the rest of the talk I'm going to talk about how we do that, how accurate that is, how fast that runs, that kind of thing. Okay, so I talked about the motivation for the work and gave you a bit of a preview about where I'm going. I'm going to talk about the method we're using. So our big contention here is that we can train a machine learning model on millions of documents on the web that talk about how to program, and that machine learning model can then be repurposed to analyze malware and generate the kinds of reports that I just showed you. So why train on the web? If you actually look at if you look at the kinds of documents that exist on the web that talk about programming, there's a lot of document data sets that are really juicy training data for a machine learning system. Like, for example, this is a post from the website stackoverflow.com. I think probably anybody who programs uses Stack Overflow, right, to go and answer your programming questions. So here somebody's asking basically, how do I log into a web page programmatically? And then somebody, there's actually lots of answers on this thread, right? But here's one answer, right? So somebody gives an answer and they say, here's some example code about how to do that, right? And so they list the API, there's a sequence of API calls here, ending with HTTP open request A, right? So if we could train a model using natural language processing algorithms to associate the task, right? The task being log into a web page programmatically with the example code. We could train over millions of these kinds of documents. We could train a model to actually automate the process of associating sequences of API calls, protocol strings with capability. So that's what we're doing. So we're training on millions of documents using the model to detect malware. As I showed earlier, we can auto-document those detections by referring back, basically citing, like you'd cite in a research paper, right? Citing the documents that actually give support for our detections of the capabilities. We can also, I'm not going to talk so much about this in this talk. If you're interested in talking afterwards, we can talk about that. But we can also boost, if you have some malware that you know what it does, we can actually boost the model's accuracy by using that labeled malware. So I'm going to talk about the data sets we're using right now in this project. We're still very much in a research phase, although we're still targeting to release in November. So right now we're using Stack Overflow. There's about 5.4 million question and answer threads that we've downloaded off of Stack Overflow. These are actually licensed under Creative Commons, so the data is publicly available and legally usable under this project. There's about 5.4 million questions that have been asked, and then each question is actually a thread, right? So there's many more documents than just 5.44 million, right? There's the question, and then there's a bunch of posts and response. We're also using a few other question and answer sites. So Super User, it's a Q&A site for power users. So these documents have a lot of information about like efficient shell scripting and how do you use VB script and stuff like that. Actually turns out to be useful because there is malware certainly a lot of malware that uses those languages. We're using Server Fault, which is a really useful IT administration site that has lots of information about network configuration, firewalls, network security, that kind of thing. And finally, Ask Ubuntu, which has a bunch of information about Linux. So those are the four document corpora that we're training our model on. So just to give some, so one might ask the question, like, you know, how often do the kinds of protocol strings and API calls that are associated with malware actually show up in these discussions, since these discussions aren't actually directly about malware. So we actually did an experiment where we took 53 malware samples, did dynamic analysis on them and also static analysis, and pulled out as many strings as we possibly could. And we saw how many of those strings actually appear in these document data sets. Actually, in this experiment, we only used the Stack Overflow data, so we'd get greater coverage if we used all 4 document data sets. So we found that rounding up 78% of the function calls appearing in the malware also appear in the question and answer sites. And on average, they appear 3,000 times or so in the question and answer sites. So this should give some intuition that if we could pull out those documents that talk about these function calls and use natural language processing techniques, we could get at the capabilities the malware actually has. Just going to check how much time I have left. Okay. So what does our model look like? The basic setup is the user creates so to define a capability in our model, instead of writing expert rules, the user writes a search engine style query into the document corpus. So for example, if one was, I'll show some example queries in a second, but if one wanted to find that webcam capability I showed earlier, one might just write a query like they write into Google, right? Find me all the documents that talk about how to develop the webcam capability. That's how you configure them. So instead of having to write like 1,000 lines of expert rules about API calls, you just tell it, find the documents, right, that talk about webcam. And then CrowdSource, our system, learns a statistical model that models what it means to implement that actual capability. And finally, the user provides, actually at inference time, the user provides samples and the system outputs yes or no. Does the sample have the capability or not? Or it can also give a probability that the sample has the capability or not. So our queries look sort of like this. Like if you want to find, does the sample transmit via ICMP, you can write a query like, well, the post should have ICMP in the title, or in these question and answer sites there's tags, so the tag should have ICMP. And that's it, right? That's the whole configuration to detect whether or not the sample is using ICMP. So you give the system this query, it pulls down the documents that talk about ICMP, learns what it means to implement ICMP, and then it can do inference on malware and say whether or not ICMP is being used. So we've actually, in terms of our discriminative model, we've tried a whole bunch of different machine learning. We tried 8 different machine learning models. We got variable success. Here's a slide where we give some intuition. This was a test where we used a linear support vector machine and logistic regression classification to detect remote desktop capability, right? So you see the red samples have remote desktop and the green samples don't, right? And we're testing to see how well we can discriminate along this decision boundary, whether or not the sample has these or not. So this is a model learned on the documents then applied to the malware, right? Overall, we applied 8 different combinations of sort of canonical text classification models to this problem. So these little acronyms are random forest, right? It's a typical classifier on documents. Logistic regression, one of the most canonical document classifiers. Linear SVM, and we tried every combination of those 3 in an ensemble. And we got these. I'm not going to go too much into this chart, but these are sort of some accuracy scores. This up is good, so this red line sort of did best, but we're still only getting it around 85% or so. So we thought we could do better by developing our own custom model, which is what we did. So the model we're actually using in CrowdSource right now is a Bayesian network. So I'm going to go a little bit into the math behind that. So Bayesian network, so if there are machine learning people in the audience, we can talk in more depth about how the model works. I'll just say it's a connectionist model and a probabilistic model, where in our case we have a 1-layer Bayesian network. So on the outer layer we have the observed symbols that we see in the malware, and then and on this inner layer we have the capabilities. So screenshot, does the malware take a screenshot or use webcam, this kind of thing. So to actually learn what nodes to include in the network, and to learn this outer layer, we use and to learn these edge weights, we use this equation. And just to give some basic, this is a beta-Bernoulli model. It's a Bayesian way of estimating this parameter. Essentially, just to give some intuition, what we're doing here is we're looking for symbols that when they appear in the document data, they almost always appear in discussions of the capability of interest, right? So, for example, in the case of IRC, right, the posts in the document corpora that we're looking at that talk about socket. Well, if you think about all the documents that have socket, the BSD sockets API call in them, a lot of those socket appears a lot of times, right, probably in discussions of IRC client functionality, but it probably also appears in a lot of other contexts too. So it's probably not the best indicator of IRC functionality, right? Whereas something like priv message, which is very much an IRC protocol string, it probably appears far fewer times than socket. But when it does appear, it probably almost always appears with IRC. So the way that we're doing the learning, we wind up pulling out these symbols that appear oftentimes with the capability. The way we do inference, so these are unobservable parameters of the model, the screenshot capability. This is what we're trying to learn, right? This is what we're trying to infer when we see a malware sample. We use a noisy OR gate to estimate those, or to infer those. You can look up in the literature noisy OR. It's a special kind of Bayesian construct. Another way of putting this is a Poisson binomial distribution, which is a special. It's a Poisson binomial distribution. This is a sort of special case that we're using to estimate the capabilities. Finally, you can do a Bayesian update if you want to incorporate prior knowledge. And we've experimented with two different forms of the Bayesian update. One in which we assume that the true and false detections were generated by Gaussian distributions, and another in which we don't make that assumption, and we use actually a random forest regression model to estimate the true and false positive rate of the system. And again, that's something we can discuss afterwards if people are interested. This is just some output from our regression model. So that's just at a high level the algorithms that we're currently using. And I guess we can say that they're performing far better than the canonical text classification model. So it was worth rolling our own statistical model for doing this. So now perhaps the more interesting part is how accurate is the system. So in order to evaluate our accuracy, we actually hand reverse engineered a bunch of malware, something like 500 samples. There's overlaps in these data, so malware that uses SMTP sometimes also appears in this bar, right? Sometimes also provides remote desktop. So in any case, we're evaluating ourselves right now on these 14 capabilities. So capturing webcam, uploading data back to the attacker, using BitTorrent, using SMTP, taking screenshots, providing remote desktop capability, logging keystrokes, using IRC, et cetera, right? So connects to a database. So actually we found a bunch of malware in our corpus that mines Bitcoins on the victim's machine, which was sort of a surprising and interesting find. So we're actually detecting Bitcoin mining as well. So this is the malware that we hand reverse engineered to evaluate how well we can automatically reverse engineer the malware. So we showed this example before. Here's more example output, right, where we're detecting HTTP transmission. And now here's our accuracy. So we've debated a lot on our team how to evaluate our accuracy. This is one measure that we're using. So some people may be familiar with area under receiver operating characteristic. It's one way of evaluating the accuracy of a binary sensor. With area under ROC, if you score 0, that means that your sensor is no better than a random sensor that's just like coin flipping, right? Like spitting out random detections. If you score 1, then you're perfect. So on most of the capabilities I just listed, we're doing really well, right? So we're close to perfect on, like, we can detect IRC clients according to our test data set perfectly, right? In some case, SMTP is we're sort of weak on, but most of these we would contend that our system is operationally useful at this point on these 14 capabilities. And actually, what's limiting us in terms of expanding to more capabilities is the hand reverse engineering process, right? So we can add more capabilities, but we need to hand reverse engineer samples and find that they actually have the capabilities in order to produce these accuracy charts. So we're going to do that in the future, and we think we can expand out to more capabilities. And I should also say that the malware that we have is written in a variety of languages. So we're testing on Visual Basic malware, C# malware, C++ malware. There's even some JavaScript rolled in there. And so our system is, because the documents that we're training on are language independent, our system can make detections across a broad range of languages, right? Because it's learning from people discussing programming, and people discuss programming in all sorts of different languages. Here's another measure of accuracy, precision and recall, right? People may be more familiar with precision and recall than area under ROC. So with precision, you're punished for false positives. With recall, you're punished for false negatives. So if you get no false positives, then you have a precision of 1. If you get no false negatives, you have a recall of 1. So our system over all 14 capabilities, if you tune it the right way, so we have a knob where you can trade off between precision and recall. If you tune it to 0.6 decision threshold, you can achieve about 80% precision and 80% recall, which we think is decent enough to be quite useful. And then the next question, how fast does it run? So this is a test on 839 malware samples. It's a histogram, and these are seconds along the x-axis. So most samples actually ran in about 250 milliseconds. So if you have an unpacked malware sample and run it through our system, you can run it in about 250 milliseconds and pull out these capability detections. So our server back in our lab has 24 cores. So we calculated that if we wanted to run it over like sort of web scale malware data, so 10 million samples, we could do that in 2 days, assuming the malware had already been. So unpacking is the big cost here. So it really depends on if your dynamic sandbox takes 10 minutes to run a sample, that's obviously a limiting factor. But in terms of doing inference and inferring the capabilities, we can do that very, very quickly with this model. Okay, so finally, I'm just going to see. So, okay. So what's the impact of all this? Why is this useful to the open? So we hope this again is an open source tool, and we're hoping that it will have a positive impact on the open source malware reversing and more generally security community. So you can easily add new capabilities. You can easily adapt to new languages, right? So I know there's a talk at Black Hat about like JavaScript malware that does DDoSing, right? We would hope that our system could easily, like we've already demonstrated, it can adapt to new platforms and languages. We could hope it would be an adaptable platform for detecting malware running on new detecting capabilities and malware running on new kinds of platforms. We can also we actually figured out sort of the math to encode our model as Yara rules. So if anybody in the audience uses Yara, Yara is a domain-specific language for detecting malware, basically detecting patterns in malware. So we actually can, in a principled way, write our model as a set of Yara rules, and then Yara will actually compute the Bayesnet decision in Yara, right? So we can export those. So if you don't want to deploy the software, you can just download a bunch of Yara rules and use it with Yara, which is it's a more popular, obviously. We have a research tool, and Yara is an operational tool, so it's nice to be able to export into a tool that's widely used. You can also do large-scale malware demographics with a technology like this. So this is a matrix visualization that we did. Down the rows, we have malware samples. So we have them labeled by antivirus label. So we use the Kaspersky AV engine for testing. So here's a bunch of downloaders, right? And then along the columns, we have the capabilities. Unfortunately, it's hard to read because they're at a 90-degree angle. But and then so the brightness of these entries in the matrix is a function of the probability that CrowdSource thinks the malware has a capability. So you wind up seeing functional clusters of malware, and you see a higher level structure to a malware corpus than you would normally see. And again, you could do this over many tens of thousands of malware samples. You could cluster the samples based on the capabilities we've detected, and you could do this kind of demographic analysis, which currently isn't really possible because right now we're all hand reverse engineering the malware. And finally, this is just the kind of output that we're generating. So it's sort of like running CrowdSource sort of feels like running Nmap over a malware sample. It just in a couple hundred milliseconds, you get a report, a high-level report about what the malware sample is doing. So here, just giving you an example of how it sort of looks and feels to run the tool. Here, I've run it over, what's the sample? Some malware sample we have in our test data set, packed.pe-patch. I don't really know what it does, right? But what CrowdSource says is that it takes screenshots and it gives these API calls as evidence for that. It also says that it does DLL injection. Anybody who does malware reversing probably recognizes this sequence, this body of API calls is probably having to do with injecting a DLL into another process. Recognizes the webcam, that it downloads files, right? And if you look at the API calls, it really looks like it probably does. Recognizes that it registers a system service, right? So that's the kind of output that you get. And we hope that people follow the tool and use it once we release it, and hopefully we get some people to participate in the project. So thanks a lot for your time. So I don't know if we have time. Is there a question? Uh-huh. Yeah. So you can dump almost anything into the tool. So you can dump a dynamic trace from a malware sandbox and extract system calls and API calls the malware is making, registry keys that the malware is touching, file paths the malware is touching, That's the source of the natural language data. Or you can drop the import address table out of the malware. You can look at initialized data where there's format strings and that kind of thing. Those are the kind of symbols that we're using to make these detections. Yeah. Yeah, please.
Could you use a similar technique to identify capabilities that were detected by your model? Can you tell if there's a piece in the binary that does something that you don't know?
Yeah, so that's actually an active area of research that we're working on. So I can talk to you about some approaches that we're trying to that, but we're definitely thinking a lot about that. We think of that as unknown capability detection, right? So like that Bitcoin example, right? We didn't know that malware mines Bitcoins, right? So we were hand reversing the sample when we found that, and then we wrote a pattern later, right? We wrote the query later. So it would be nice to be, so right, I think what you're asking is it would be nice to be able to not have to do that, right? To have it automatically detected some new capability without having. Yeah. So we have some preliminary stuff to do that. It's not in the presentation, but if you want to come talk to me afterwards, I can tell you about what we're doing there. So yeah, no problem.
What are your plans for including mobile malware?
So we've done some preliminary tests on mobile malware, and the results are promising, as I think you'd expect based on how the method works. That's not something so we need to scope our effort, right? So that's not something we signed up for in terms of releasing our product in November. But it is something, certainly for the long term, that we plan to pursue. Yeah.
So your need for an unpacked sample implies you're working off the imports table, correct? For the function names?
So we're not just working off the import table. We're also working off of basically throw any unpacking technology or malware analysis technology that you have in there, right? Extract, so if you're using symbolic execution or a dynamic execution environment or dumping, running strings, right? All that stuff can be processed by the system. All the system needs is a bunch of stuff, right? A bunch of symbols and a bunch of protocol strings and format strings, right, that have been extracted, and then it can do its inference. So
you're working off the strings that make up the function import table then. Do you have a way to handle importing by function number? Ordinal
number? No, we don't. But so we don't see that as part of the machine learning problem, right? We see that as part of the unpacking, the sort of data preparation problem, for better or worse. Okay. So yeah, but I think that's a reasonable thing to bring up. Yeah.
Thanks.
Yeah. Yeah, I should have said that. So if I'm answering your question right, we're using 400 binaries that are known benignware to test against, and making sure that we're not. So that's actually how we get our false positive measure, is by making sure that it's not flagging falsely binaries that we know definitely do not show the capability. So that's how we measure that. Yeah. So those corpora are actually publicly available on the Stack Exchange website as XML dumps. So that's something we've thought of in terms of, that's just a logistical question about how we release the tool. Like, do we give people 20 gigabytes of text, or did they download it themselves? I'm not sure, but they're publicly available. I guess the only thing, we're doing stemming and tokenizing. So a big part of the research is how do we stem. There's sort of classical natural language processing problems that we're engaging. So the corpus that we actually use has been transformed with. We've done word count vectors and all this. So we need to figure out how to distribute that once we release the tool. But yeah. It's true. Yeah. So it's a very lightweight tool, except for this dozens of gigs of text that you need to install. Yeah. Okay. Well, thanks a lot, everybody.